Okay, so at this point in time, you should probably already know the difference between two separate isotopes. Remember that isotopes are the same exact element. The only difference is that they have different masses associated with each one. And the reason why they have these different masses is because of the fact that they have differing amounts of neutrons. Now we're going to get into how to detect and actually identify every single isotope for the same exact element. The way that we do that is with something called mass spectroscopy, which is simply a technique that we literally use to just identify isotopes and check their abundance. Now this word abundance just literally means the amount of each isotope. So this is what your typical mass spectra looks like. As you can see, we have two separate signals coming in on this graph. We have this x-axis and we have this y-axis, and we see two separate peaks. Now, each one of these peaks represents one separate isotope. So just from looking at this graph or this mass spectra, we know that we're working with an element with two isotopes. Remember that these peaks represent the same exact element. The only difference is they're going to have different masses because these two isotopes will have different amounts of neutrons. Now then, first of all, let's read the y-axis. For the y-axis, you can see that it is labeled as relative abundance, and we already spoke about this word. It just means the amount of an isotope that exists in nature. So obviously, the higher the peak goes in terms of the in terms of the y-axis, the more abundant said isotope will be. Now, this number is either going to be represented as a number or a percentage. A pretty easy way to tell is to just look at the sum of the values. Since you can see right here that the sum of the abundances ends up being 100, we can tell that this graph is representing everything as a percentage. If it was 0.1 or 0.2, then obviously it would be considered as a number. Now, this graph is obviously not set to scale, especially with the numbers that I'm going to give, but this peak right here has a relative, This peak right here has a relative abundance of around 20%, and this peak right here has a relative abundance of around 80%. Now then, we can obviously convert these percentages back into numbers by simply dividing by 100 or moving the decimal point over to the left twice. So this 20% would be converted into 0.2, and this 80% would be converted into 0.8. Okay. And again, the relative abundance is found on the y-axis. Now for the x-axis, that is going to represent the mass or the weight of each isotope. Now, the x-axis will be labeled in a variety of different ways. You'll either see it as relative mass, atomic mass, mass to charge ratio, or m over z. As you can see from this graph right here, or this spectra, it's labeled as m over z. But they all essentially mean the same exact thing. It's just the mass of each isotope. So if we were to look at this spectra right here, you can clearly see that this isotope right here on the left weighs 10 atomic mass units. And this peak right here is at 11 atomic mass units. So at this point, we can essentially figure out which element this mass spectra relates to, because we know that the mass should be from around 10 to 11. Now hopefully you have a periodic table on you, and you can see that the only element that really fits this description is boron, which is B on the periodic table. Boron has an atomic mass of 10.81 atomic mass units. Now if you notice, this mass that you see on the periodic table is not 10 atomic mass units, nor is it 11 atomic mass units. It's sort of something in between. And hopefully you should also take note of the fact that this atomic mass that you see leans a little bit further to 11 than it would to 10. And the reason for that all has to do with the abundance of each isotope. The isotope at 11 has an abundance of 80%, while the isotope at 10 has an abundance of around 20%. What that means is more boron atoms on average will weigh 11 atomic mass units versus weighing 10 atomic mass units. So the average of all the borons will be roughly around this mass right here. Okay, so now that we know how to work with mass spectra to actually interpret a mass spec and identify an element based on said mass spectra, we're now going to be able to calculate the average mass of every single element on the periodic table. Now, the average mass is simply the weighted average of the mass of an element, and the reason why we have these averages is because, remember, isotopes of the same exact element exist. And so the way that we calculate the average mass is by using the different masses and abundances of each isotope. Once again, remember, isotopes of the same element will have different masses since they have different amounts of neutrons, and they will exist in different abundances or different quantities. Now we have a specific formula for average mass, which is simply average mass is equal to m1 times p1 plus m2 times p2 plus infinity and beyond. This formula is entirely dependent on how many isotopes you have. So when we're defining all the variables, we use m sub n's and p sub n, sorry about that. Now, our m values, at least in this formula, m1 and m2, are going to represent the atomic masses of each and every isotope. That's easy enough. Obviously, if we have a third isotope, then that would just be labeled as M3. Now our P values, our P sub 1 and our P sub 2, these are going to be the abundances of each isotope. So whatever the abundance of the first isotope is, that will be the P1 value. Whatever the abundance of the second isotope is, that will be the P2 value. Quick note about percent abundance, however. If it's given as a percentage, you must revert it back into being a number by simply dividing it by 1,000. Sorry, not 1,000, 100. So if you have something like 90.8%, you would obviously convert it back to a number by dividing it by 100 to just making 0.908. Now let's actually take a look at an example of calculating average mass, that being boron. So boron has two main isotopes associated with it. We have B10 and we have B11. B10 has an atomic mass of 10.013. B11 has an atomic mass around 11.009. And in this table we have the abundances listed right here, 19.8 for B10 and 80.2% for B11. Just as a quick check, you can clearly make sure to check if the abundances are correct. If you were to add up 19.8% and 80.2%, you would see that you have 100%. So these abundances are in fact correct. Now, we actually have every single one of our variables. We have our masses of each isotope. So I'm going to label B10's atomic mass, this one right here, as M sub 1. Sorry about that. And I'm going to label B11's atomic mass as N sub 2. So this is the mass of my first isotope, this is the mass of my second isotope. Next up, we have our abundances, our P values. However, the main issue with these right now is that they are in percentage form. So I'm just going to easily convert these into decimal form by dividing by 100 or just simply moving the decimal point over 2 times to the left. So this will now be 0.198. And this will now be 0.802. Okay, so now I have every single one of my variables, so I can easily just calculate average mass. So average mass is equal to M1, which is 10.013, times its percent abundance, which is 0.198, plus M2P2. So this is going to be 11.009 times 0.802. You do some fun, wacky math, and you end up with an average mass of 10.81 atomic mass units. Now, this is the average mass for boron B. Oop. Now, there is actually a way to verify if your answer is correct or not. Right now, you should be looking at your periodic table and checking to see what the mass listed under boron is. If you look at boron on the periodic table, you'll clearly see that the average mass is also 10.81 atomic mass units. Because of that, we know that this calculation is in fact correct. So anytime that you're calculating the average mass of an element, you can always look at the periodic table and check to see if your final answer is correct. If your final answer is incorrect, that obviously means you need to go back and fix something around here. Okay?